My name is Jake. I work at a search engine that builds an operating system. I'm here to talk about multi-platform, but in a way that's not the traditional way that multi-platform is talked about. So there's probably a bunch of other talks in this track which are emphasizing Kotlin multi-platform being used for different actual platforms. And what I'm here to sort of dispel is the notion that you only can use Kotlin multi-platform to target, to share code across Android, iOS, and the web. This is not actually true. And so I'm going to start with JavaScript. Why would you potentially want to run JavaScript on Android? First off, browsers are a ubiquitous thing, and most apps have an associated website with them. And because JavaScript runs in browsers and browsers are everywhere, you have the ability to very easily run JavaScript on Android. And this enables code sharing. JavaScript is sort of like the original multi-platform language that we had at our had available to us in order to use. And that's also true of the other platforms that we usually associate something like multi-platform with. iOS has browsers. They have a built-in something called JavaScript core to allow you to easily run JavaScript on iOS. And then servers also run on JavaScript. Maybe your backend is written in JavaScript running on Node. And so in the same way that you think about a backend written in Java and sharing a library with your server that's written in Java, the same is true of Node. If your server is written in JavaScript and there's a certain piece of logic that you don't want to re-implement for whatever reason, there's really no reason that you shouldn't be able to share that. And it could be all or a subset of these, right? Like most apps come in flavors where there's at least 2 mobile components and probably a web component. And so out of the box, there's going to be the ability to have sharing. There may be other business-specific reasons that you might want to choose something like JavaScript. When you place an APK on the Play Store, there's a certain turnaround time associated with shipping new code. It's probably a multi-day or potentially even multi-week process, depending on how large your user base is. And if you need to ship some updates very rapidly, that can be challenging, disrupting a train schedule that you have, and even just getting all of your users to actually take the update. Technically, we have the ability to ship DEX code out of band from the Play Store, but this is actually not allowed. The terms of service of the Play Store explicitly prevent you from doing this. But that's only for DEX code, and we actually can do this for JavaScript, which is in this weird gray area because it's essentially the same thing. You're allowed to use JavaScript to change the functionality of your app with these out-of-band updates. Also true for iOS, and this is really specifically because if you ban this, then browsers can't be a thing. And so there's a weird gray area, but it allows this instant availability of updates to your users. A concrete example of this in the Cash app, where this is a peer-to-peer money transfer app that operates in the United States. And the United States, you have to get money transfer licenses in almost every state in order to actually to transfer money. The problem is that every state differs on requirements. This is not a problem in and of itself, but what can happen is here I have a payment that I sent to Alec, and it says I sent this payment. But if I sent this to a nonprofit, a state can come and say, actually, you can't use the word payment, you have to use the word donation. This is not a problem. You update your strings, to go out in the next train. Where the problem comes is that oftentimes they say, well, you have 7 days to do this, or your money transfer license is suspended until you fix it. And so on the web, this is easy, right? They just do the string and deploy. On Android, it's maybe a day, multi-day process getting it rolled out. Not terrible. iOS traditionally has been the roadblock here. Their review times were a lot higher. You can pay for expedited review, but it's not guaranteed. And so there's a business need now to have a way to update logic in the app faster than the app stores can provide. You can also think of maybe syncing. We could do this on the server side or whatever, but it starts to become prohibitively expensive. There's tens of thousands of payments, millions of users, couple of these, like states come and change this a few times a year. There's associated costs of like downloading the update, and it adds up to like hundreds of terabytes that you're just wasting for your users per year. And also it doesn't solve the problem of localization. What happens if the user changes their phone to Spanish? Are you gonna resync everything with the server? Probably not. Maybe you sync templates, but the problem here is not actually we wanna change the string, we wanna change the logic associated with rendering the string. And so you can't do that just with updating the server. And you still have the manual localization problem. And so Cache, we turn to JavaScript for this. We basically take a blob of JSON, pipe it through a JavaScript engine, and get another blob of JSON out, which has the rendered strings. And so this still comes with like manual localization that has to happen in the JavaScript, but now we have the ability to update the logic so that when Florida comes and says this has to say donation if it's to a nonprofit, the JavaScript can actually include this logic. This can be embedded in the app, so you don't have to be, once the user has the app, they don't actually have to be online and the JavaScript fetched from a remote server. It's embedded in the application so that it works out of the box. But then the benefits really come from the fact that you can host this on your server, and when a state comes along or your business requirements change that you need to change how it's rendered, you can just propagate that down the next time the app syncs with the server. So that's JavaScript, like some potential business use cases that you might have for embedding JavaScript. Let's talk about native really quickly. In the same way that how JavaScript is able to run everywhere, native is really able to run everywhere as well. Definitely, a lot of Android apps have native code in, usually pulled in from libraries. iOS is a native platform. On your web browser, you can actually use a library called mscriptin, which will compile your native code to JavaScript, or WebAssembly is a new emerging thing, which is sort of like a bytecode-like virtual machine that native code can target. And then your servers can also be written in C, C++, or Rust. For Android specifically, a lot of libraries come with native APIs. If you want to interface with something like TensorFlow and you're not actually using one of the wrappers that are provided for you, you'll have to drop down to native and then interface it with it yourself. And then in terms of like specific business cases, just sticking with the Cache example, barcode scanning is part of the app, and you have to, like, barcode scanning is actually somewhat tricky, being able to recognize the barcode, the orientation, and then parse out the data with all the how lossiness of how images work. And so a lot of the libraries that provide this functionality are in native. And so these are use cases why you might choose JavaScript or Kotlin embedded in your Android application. I'm not saying that you have to use these two technologies, but the use cases are definitely there for some apps. So let's start talking about Kotlin a little bit here. Traditionally, Kotlin's thought about as just a compiler for Java bytecode. Kotlin files go in, class files come out. A bunch of multi-platform talks at this conference as well. And if you haven't heard about it, it's basically you can change the backend for the compiler and allow it to emit JavaScript or native libraries, assuming that the input to the compiler is platform agnostic. If it's just pure Kotlin logic, then it should be easily translatable across these targets. You could still have platform-specific Kotlin, like the Kotlin that we write when we reference an Android type or a Java type in the Android or Java packages. That's platform-specific Kotlin. Platform-agnostic Kotlin, which would be the leftmost thing, it can only reference either Kotlin APIs or libraries that have provided a Kotlin, like common Kotlin APIs. And those produce our three associated platforms: JavaScript, Java bytecode, or native libraries. Kotlin multi-platform in a really small nutshell, kind of assuming that everyone understands that this is a thing. Other talks at the conference are sort of covering it more in depth. And I'll move on and talk about abstractions a little bit. So abstractions allow us to interact with something at a higher level than its implementation detail, or even potentially hide implementation detail. This is a retrofit interface that we can then program against in the same way that you might program against a list interface. And while they represent very different things, it's the same mechanism here where the retrofit interface is being backed by how retrofit works, and then talking over a network to a remote server. But potentially we could implement that interface ourselves for something like tests. And just like lists, we might choose based on what we're doing to use something like an array list or a linked list. And so, like I said with retrofit, you might use retrofit out of the box to talk to a remote server, but you also might implement it yourself. And this is sort of a spectrum where the interface doesn't dictate anything about how the backing implementation works. So this could be anywhere from locally in memory, it could be talking to a database on the file system, peer-to-peer, all the way up to HTTP. All right, so those were kind of three separate things that now I want to tie back together and see if you recognize the trick that I'm about to pull. We made the case for JavaScript and native code being something that you might use on Android in certain cases. We talked about how Kotlin, multi-platform, allows you to compile Kotlin code for the 3 different backends that it supports. And then we talked about interface abstractions and how they let you program against something without really knowing the execution context of the implementation details, whether it's locally or maybe remotely. So these 3 separate things we can combine together to make a pretty neat trick. Given an interface, compiled with normal Kotlin JVM, produces a class file that we can program against. Given an implementation of that interface, we can do the same thing, Kotlin JVM, produce a class file, and then these 2 things can live in the same app, just like our normal code, and talk to each other. But if our business requirements of our app change such that we need to use something like JavaScript or native to fulfill them, by using an abstraction, using the different backends of the Kotlin compiler, we can take that same implementation and move its execution context to be JavaScript or native, and then allow our interface through something like a JavaScript bridge or a JNI bridge to talk to that new implementation without having to change the rest of our code base. So we can start off with like the normal dumb thing that we do every day, creating new interfaces and new classes just in regular Kotlin. And then as business requirements change for whatever reason, we need to be able to update something dynamically, push through the server, so JavaScript becomes the right choice. It becomes easy to move that implementation there and then allow that functionality to happen. Or we're interfacing with, we need higher performance out of this if it's something a little more computationally heavy, or we need to interface with a third-party native library. It becomes trivial then to move the implementation to native without changing the interface. So really quickly, I want to build like the world's worst implementation of this, where we basically do the string rendering trick of cache, and we have a little selector to choose which backend it's going to run on. The first one is the absolute easiest. And so what we're going to do is replicate either sending a payment to a human or sending a payment to a nonprofit, and we want to see that second line string change. One sort of caveat about this and how we structure our project is the interface and the implementation has to be separate, because the interface is going to be what we program against in our normal Kotlin bytecode targeting code, and the implementation has to be movable, so it needs to be in its own module. So we're going to define a module that contains the API for our thing that renders a payment. This is just a simple interface. I'm starting extremely simple, just like rendering that single second line, which takes the tag, like the username of the person, and then whether or not they're a nonprofit. And it just returns a string. The implementation, the second module, is just going to be, this is going to be that common Kotlin code that has no dependencies. So the only thing it can refer to is the Kotlin standard library. We're going to use its functionality to just build a string, switch on whether it's a nonprofit or not, and put in donation or payment, and then append the rest of the string. Obviously not doing any like localization or anything here. This is just a example to show the mechanism, not actually like a real implementation. And so again, no dependencies other than the Kotlin standard library here. We can also write tests in this module, which is pretty cool. Just instantiate our implementation and then call it twice and make sure that it's actually doing the right thing. What's cool about this is not that it's a test, which we should have written anyway. It's that the Kotlin multi-platform plugin will run this test on every backend that we end up targeting. So if we just start with normal Kotlin JVM embedded in our app like any other class, it's only going to run this on the JVM. As we start to add other potential backends like JavaScript or native, the Gradle plugin will actually run your tests on those different platforms to ensure that the behavior remains consistent, so that the interface you're programming against sees the same behavior regardless of where it's running. This is also especially important if you're interfacing with other libraries that are multi-platform, like if you're using Ktor to talk to a remote network service. you want to be sure its behavior remains the same across every platform. And you only have to write this test once. And then finally we have the app, which is going to pull in both of these modules just to start with, like normal dependencies, but then later as JavaScript and native. So to start with, for just normal dependencies, we pull in the API, the thing that we're going to program against, and then our first implementation, which is just the, by default, this is going to depend on the bytecode version. Grado's going to select the version that makes the most sense of this platform, and because this is an Android module, it's going to select Java bytecode. And then we'll get to JavaScript and native in a second here. I want to start getting just the Java bytecode version working. Create like a real dumb UI, inflate our layout, set a click listener on the run button. We switch between which thing is checked, and then we're just going to render we're going to instantiate our 3 different implementations, just starting with the default one of Java bytecode, and then just render our text. So fire this up, and it's going to work because right now we're doing nothing special. We're just doing normal dependencies, normal Java bytecode. Let's start to get tricky. Let's pull in JavaScript now. There's a bunch of different JavaScript engines. Which one you choose for Android really depends on what your requirements are. V8's sort of this big, huge monster that lives in Chrome. Massive performance, but massive size as well. There's a bunch of different smaller ones. One that we've had a lot of interaction with is called Duct Tape. It's got a cute little text logo that's, I think, is supposed to look like a roll of duct tape, but it just looks like a roll of toilet paper to me, and I can't unsee that. So, and there's new ones coming out. There's one called Quick.js, which just came out about 6 weeks ago, which is even smaller than duct tape. It has almost like 5 to 10 times the performance of duct tape. But we're going to look at duct tape because this is something I've worked with historically, and we've actually written a library around it for Android. A cool thing about this library is it's going to enable us to pull off this trick without much effort. And so in the documentation for duct tape, it has this example of how you talk to the JavaScript from your Java or Kotlin code running in the JVM or on Android. And this example code uses a bunch of the things that I've been talking about. We started off with an interface that you define, which represents the API that you want to talk to. On the JavaScript side, you could pull in like a JavaScript file and pull it into duct tape, but basically you just have to create an object which mirrors that API. And so here we're creating an object that has a function from hex, which takes in a string and returns an unhexadecimal string. Then in a very retrofit-like way, we just ask it to create an instance of this interface bound to a particular variable that lives in the JavaScript engine. And then we can interact with it without even really knowing that it's backed by a JavaScript engine. So if we go back to our implementation, we want to get it running on duct tape. We can update its build so that it doesn't just target JVM now, it's going to output JavaScript. And you have to select whether it's like Node.js or browser, and it sort of changes how the JavaScript is rendered or emitted. For this example, because we're running inside not really a browser, but not really a server, duct tape kind of acts like a server. We choose Node.js. And what this is going to do is produce a sibling jar next to the one that has Java bytecode inside it. And if you peek inside that jar, it's going to have a JavaScript file, and that JavaScript file is going to have a bunch of stuff inside it, which you don't really need to look at, but it is the same logic that we implemented that now runs in a JavaScript environment. We can zoom in here and see the core function, our second line function, which is interacting with this string builder API that we don't see. But one thing that's sort of unfortunate that starts getting in our way is the name of this function is second line underscore and then a hash or some garbage. So this is going to prevent us from being able to match it on the Java side, like duct tape being able to match it. And this is because JavaScript doesn't have overloads like Java or Kotlin does. Every function has to have a unique name, or otherwise it's only there can only be one. And so we can just tell the Kotlin compiler there will only be one function named second line, and so it will emit that hash and emit exactly what we specify. And so that fixes that. Now, in the app implementation, we want to use duct tape to talk to this JavaScript rendered implementation. That's as simple as creating an instance of duct tape, loading the JavaScript file. I'm like hand waving a little bit over how you get the JavaScript file into your Android app. You can do some complicated Gradle magic or just copy paste it, which is what I did. And then we need to create an instance of this object. JavaScript has a module system, but it doesn't have packages. And so there can be name collisions, and Kotlin tries to replicate this by creating objects for each package. So we have to like fully qualify everything we talk to. You can again use annotations to like change these names and make them nicer. But since you only do this once, it's not really worth it here. And then we call into duct tape to create an instance of our interface. Now with the second branch of this when implemented, we can run the app again, switch to JavaScript, and after like a second long delay, it's going to render exactly the same. This code talking to Java, like setting up the JavaScript is kind of boilerplate and redundant, and it's really a pain, but the effects that it produces are pretty cool. I mean, we basically did 5 minutes worth of work, and now we're able to move that class to render in a different context. It would be nice if there was something a little higher level that knew how to link these things automatically, like a library. We could just say, here's my interface that's coming in, here's my implementation, and it would link everything together. It would do that like package name thing, and you wouldn't have to worry about it. I'm not announcing this library existing, but like if this is something you want to do, you probably want to look into building something like this. And this becomes doubly true for native. There isn't anything magical like duct tape. I mean, duct tape did all the heavy lifting of getting that JavaScript interface bound to the implementation running in the JavaScript engine. But native, there's not really anything like that. You basically have to just do the JNI boilerplate yourself in order to talk over the native boundary to the native compiled version of your class. And so you can write this by hand, but you really need something that would generate this automatically for this to be an effective strategy. But if you do write it by hand, and you do add native to that module and pull it into your Android app, it's going to work exactly the same way. It's pretty cool to see this in action. I think it's pretty cool to see this in action. It didn't take a lot of effort to do this. There were no like great leaps forward in how Android apps are being built or how we design these systems. Like this is just normal Kotlin multi-platform. It's normal interfaces and implementations. There are some roadblocks, however, to this being an actual practical solution that you can implement. The first is that JS name dance that you're really required to do on every API. It's only APIs that have parameters, but like I don't know why you would have API that didn't have any parameters if you were using this, because it's really about moving something that does work, and work needs inputs. Even with a library managing both sides, like that hypothetical Kotlin JS library, you really need something like a Kotlin compiler plugin that's just where you can annotate the interface as like, this is going to have implementations which are moved, and it will generate all of those annotations for you. It's not really viable because Kotlin compiler plugins aren't a stable thing yet, and so that's like a few years off at least. There's also that JavaScript like bootstrapping snippet, which is a little bit annoying. Again, this is something that could be handled with a library tied to a compiler plugin. I also didn't show the packaging aspect. It's more than just getting the JavaScript file out of that jar into your Android application. You need to do like a combining and minification step, because you have a dependency on the Kotlin standard library, which is some like multi-megabyte JavaScript file. And you really want those combined together into one file and then minified so that only the stuff that's needed is used to get that down to like kilobytes instead of megabytes. Basically the same trick we do with like R8 or ProGuard for our Android apps, but for the JavaScripts. And then for the native side, like this is just tons and tons of boilerplate. Like everything, you have to forward all the calls manually, deal with the JNI side, like the native side, you really need something like a Kotlin compiler plugin to produce this. You could probably do it with an annotation processor, but by virtue of the fact that you need a compiler plugin for the JavaScript stuff, you might as well just do the same thing for JNI. But ultimately, the cost of this is relatively low for the ultimate value that it provides. Again, not every app is going to have the need to move parts of its code base into JavaScript for, say, dynamic updates or into native for some performance reasons. But if you do have that, the ability to do so relatively easily is a pretty cool feature of Kotlin Kotlin multi-platform that we don't really think about. When you talk about Kotlin multi-platform, it's usually in the context of multiple platforms, but really every platform that you could potentially run Kotlin on tends to have the ability to run multiple different languages. And so for what you get out of this, for how little work it is, it's pretty cool. Those are like the immediate roadblocks. There's some more complicated ones that have solutions. One is like, I started this with the simplest API possible, just render that second line with 2 parameters and produce a string. But you don't really want to do this because the cost of doing that is very high. And you don't want to be like unpacking all these objects that you have to pass them as individual parameters. You likely already have something that represents, in this case, a payment, and then you want to get out multiple things, not just a single string. So we would probably want to have this be like, here's a payment object which has all the information you might need, and we return like this payment rendering object which has, you know, like 10 different strings that we might use depending on the context and which line of the UI is actually showing. And so you can do this today. Duct tape doesn't support this, but it could be added. JNI does support this. You can pass references across. The problem is that when you go through this boundary, you need to access like the fields and the other objects inside this, in this example, payment. And so you wind up crossing the boundary multiple times in order to do things like get these individual strings out and turn them into something that native code can understand or JavaScript code can understand. And so instead of paying the penalty of like jumping down into native code and then back up once, you wind up paying it tens or potentially hundreds of times. If we go back to looking at like trying to draw a corollary to retrofit, retrofit has this problem as well, but you don't think about it in the same way because you're crossing a bigger boundary that forces you to encode things in a different way. Like I can't just hand a pointer across a network boundary. I have to serialize that reference, whether it's this user object or an image for a request. I serialize that to bytes, pass it across this giant boundary, and then the server is going to deserialize it and interpret it. We can do that same trick here if we need to. And so this complex payment object can go through a serialization step to turn into a JSON blob or a set of bytes, cross the bridge, be deserialized by the same implementation, but running on a different platform. So Kotlin X serialization is a serialization framework by JetBrains for Kotlin that is multi-platform. And so you can write it can do the same trick that we're trying to do, which is move serialization strategies to different platforms. You don't have to write like an encoder and decoder in native and in Java or in JavaScript. Kotlin X serialization can do that for you. Then you have a real object which has all of your properties in native or in JavaScript where there's no penalty to unpacking it and pulling things out. And you can do the same trick round tripping back for your return objects. This sounds a bit heavy. It's actually not as heavy as it seems, but there's even ways to optimize it beyond that. If you really wanted this to be a solution, Kotlin X serialization is not a JSON serializer or a protobuf serializer. It's more a framework for writing serialization strategies, two of which, JSON and protobuf, just happen to be provided by default. It's a compiler plugin which inserts hooks into your classes where you can then serialize to any format. And so you could be really clever, and in the process of serializing, instead of serializing to JSON or protocol buffers or just some representation that you have to unpack, you could serialize directly to the representation that would exist in JavaScript or native so that there's no deserialization step on the other side. Then you're just paying that cost once, crossing the boundary, JNI or JavaScript or native could then talk to that object directly because it's already laid out in the right like structure. It could then pass the result back, which would then need deserialized from the memory structure to whatever exists in, like your associated object on the Java side or Kotlin side. But then you only have to pay this serialization penalty twice instead of 4 times. But ultimately, like, payment rendering is, I think, an interesting example because it's one that actually exists and actually shipped. But this is not meant to be like a really cheap bridge to cross. This is a solution that you take a chunk of work, you throw it over the wall, and then it will eventually come back to you in some amount of time. You don't want this to be happening like once per frame, or let alone tens or hundreds of times per frame. This is meant to be akin to something like a retrofit interface where you're like making this expensive call that might take hundreds of milliseconds or even a second. And so the cache use case, the payment rendering use case, was like a business requirement that had to happen. But ideally, this is something that would already necessitate being asynchronous. And so having like a suspend keyword on this interface is, even when it's just implemented in Kotlin and only running in your app like as normal bytecode, that's a good indicator of like the right level of abstraction for being able to move the implementation. It's not something where you just want to call into a method and it do like a square root and a rounding and then return the number to you. Like that's not enough work to move. So this being an Android conference, I framed this problem from the perspective of an Android device where you're writing this Kotlin code and then you have the need to move it to JavaScript or to native, and then your Kotlin JVM code needs to talk to either of those. But nothing about this approach is really specific to that viewpoint. So for example, if you have a server that's written in native code, but needs to call into a JavaScript engine, there's nothing that would prevent this same trick from being used there. Or even potentially native code that's running in like WebAssembly, which is an isolated context from like where JavaScript normally runs in your browser, that has to call over into JavaScript. It has to go through this like boundary that it otherwise has to know about, whereas something like this abstraction could hide that from either side. The inverse also true. If you have a node server in JavaScript which needs to call out to native code, that could totally work. And then calling into the JVM from either JavaScript running on your backend or native code running on your backend or anywhere. You get this nice little like symmetric triangle where it doesn't matter from which perspective you're looking. If you have the need to call into one of the other two backends, a framework like this would allow you to do that with relatively low overhead in terms of the overhead associated with actual runtime, but even the overhead associated with maintaining a solution like that. So it would have been a great slide to have like a nice triangle logo of some like library I was announcing, compiler plugin that did this all for you. But it's really not ready to be like a general purpose solution. You have to have a real hard business case for doing something like this because there still is a lot of associated work, manual associated work with it. But you're definitely able to pull it off. And then in theory, it will only get easier as things like compiler plugins become stable and allow you to automate the parts of this which are currently very tedious. And so to prove that this kind of wasn't a gimmick and actually works, the sample does actually work. All 3 backends do actually work. The video is a little choppy because you might have noticed I didn't have a suspend modifier on the interface. All of this is running on the main thread, so whenever you're doing JavaScript or native code, you're essentially blocking the main thread for a couple hundred milliseconds. I might try and open source this. The problem is that I kind of cheated on how you get the JavaScript and the native code into the Android app. I didn't actually build it in Gradle. I just kind of copied it because it's complicated. So maybe I'll try and clean that up and actually open source this. But I don't expect this is something a lot of people will walk away from this talk and be like, yeah, I'm going to go take my whatever implementation and move it to run in JavaScript. Because you would know if you had the requirements to need to run something in JavaScript to run something in native. It's really about if you have those requirements, if you need to run something in JavaScript or native, you don't necessarily have to abandon, like the Kotlin that we've grown to know and love. You can reuse the work that's being done for traditional multi-platform and target just a single platform. So to summarize, JavaScript and native code, they have their place on Android, whether it's special business requirements, performance reasons, interfacing with third-party libraries. Some apps contain JavaScript, some apps contain native. That's always going to be a truth. Kotlin multi-platform gives you the ability to actually use the different backends without multiple platforms. And then, like good software engineering, just abstractions allow you to design your code in a way that changing where the execution context of implementations of your interface are running is something that doesn't have to dramatically affect the rest of your code base. And so when something like this makes sense, you can actually turn to Kotlin and it can offer a solution that's pretty clever. And that's all I got. Thank you.